Hi everyone. Today I'd like to talk about tabular learning, especially exciting breakthroughs with skrub and foundation models. So over the years, we've seen breakthroughs in AI, but mostly on text and images. And yet the most precious data is in tables. So what's special about tables? Well, here is a typical example. So what you can see is that you have multiple columns with different data types, and you typically have categorical data. And so those columns are of different nature with different data distributions. And you might have missing values, as you see here. So how do we work typically with this data? Well, we prepare it. By prepare it, I mean that we count, normalize, encode, transform everything to numbers. And the reason we do this is it facilitates statistical modeling because it's much easier to model objects that are numerical because we can have continuous interpolation between them, just as shown on the figure here. But really, the problem is that this data preparation is absolutely exhausting. So my agenda is to build better learners that minimize data preparation. And here, when we think, less feature engineering, we think, well, deep learning has done this to, for instance, uh, vision. So will it save us with the kind of data we have? Well, a few years ago, we ran a benchmark on the latest, at least back then, deep learning methods. And what we found is that tabular on tabular data, tree-based methods outperformed deep learning architectures that were tailored for tabular data. And so what you see here is the figure that we had back then, and you can see that not only do tree-based methods perform really well, but also, they cost much less time. So they're actually, very easy to use. You just download scikit-learn or XGBoost, and you run it on the data, and it works better than complicated things. So why is that? Well, back to the properties of the tabular data. What we have is that we have non-Gaussian marginals, so marginals with distributions that are not Gaussian, and categorical features. And the inductive biases of the trees work really well with this because they make decisions that are aligned with the axis. Typically, they're going to choose one feature, so that means choosing one column, and then they will adapt a threshold on this column and then choose another column and adapt the threshold on the other. So this is really important for the data we have because each column is meaningful. And on top of this, what we found, what we showed in the paper, is that the decision functions that we're trying to approximate are non-smooth. And the trees, because they're just fitting local thresholds, they approximate really well non-smooth decision functions. So the challenge that we have is that in typical tabular data, the natural geometry is neither smooth nor vectorial. So deep learning methods don't work well. I'll come back to internal neural networks, but first I want to do a deep dive on some specific challenges of tables. And the first one is missing values. They're quite frequent in health and social sciences. And here the challenge is that the missing value token, often written NA, is not a number. So my typical model doesn't know what to do with it. So the classic approach is to do imputation. The idea of imputation is that you're going to fill in the blank with likely values. However, this is not statistically sound when the missingness is informative. So for instance, if you have people who fraud, who purposely do not report information, if we start filling in the information for them, we may be washing out useful information in the data. So we did a bit of a theory on this, and what we showed with a very powerful theorem is that for prediction, if you have a very flexible learner, asymptotically, it can give you the optimal prediction for all missing data mechanism and almost all imputation. So it means that a very flexible learner is what's important. And more recently, we did some empirical work, some heavy empirical work, and just to summarize it, what we find is that imputation is useful, but it comes with diminishing returns. So better imputation is slightly useful, but often very costly. So the thing is, some learners can actually handle directly missing values. For instance, the tree-based learner. So if you think of how a tree is built, it's a set of binary decisions. And so the learner can actually special case those binary decisions for missing values. So is the 10th feature below minus 1.5? Yes, no, or is it actually a value that's missing? So this is the strategy that's used in XGBoost or in scikit-learn's his gradient boosting classifier. And what we showed empirically is that this works very well on real data. And one of the reasons is it actually can adapt very well to all kind of missingness, including informative missingness. So what happens, one of the challenges is when you have string entries. So typically open-ended string entries. For instance, some employee position title that I'm listing here. Now, the challenge is that these string entries can have very high cardinality. And this breaks the typical way of dealing with categories. I mean, these string entries cannot easily be turned into categories. So the approach that we take is to consider really them as string and to model substrings. What you find is that in many of the data sets, the substrings are meaningful. So there is repeated substrings, and these repeated substrings carry the information. They may be repeated because you have some notion of latent category that you're not seeing. They may be repeated because you actually have categories, but there are typos in it. And so what we do is with that, we model these substrings and we find the repetitions in the groups of substrings. So basically, we find latent categories, and this can be done by looking for latent factors. And what I'm showing you here is those latent factors. So what you can see is that you can see the column that I showed you previously that's encoded on 10 latent factors. And you can see that each value is encoded in a small number of activations of latent factors. And so those latent factors are estimated automatically. So what's interesting here is that we have found latent categories directly from the data. And those latent categories, we can actually give them meaningful feature names, which is to find the words that repeat often. And so what we have here is something that looks like a categorical encoding, but with the categories that are directly estimated from the raw string. So we call this the gap encoder. It stands for gamma Poisson, which is the technique that goes behind the estimator here. Okay, so we have, for each column, we have a different strategy that we can deploy. And in practice, from a coding perspective, it becomes tedious because, I take one column, I do one transformation. I take another column, I do another transformation. And so we have a new software that's called Skrub that's designed to facilitate preparing data for machine learning, especially tabular data. And so Skrub comes with an object called the vectorizer. And the vectorizer is your typical scikit-learn object. It can fit data, it can transform data. And the way it works is that you give it a table as a data frame, and it will fit it, for instance, finding those latent categories, and it will transform it into a vector of numbers that is well suited. And so the way it does this is it applies different heuristics for different columns. So typically, if I have low cardinality categories, it will do a standard categorical encoder. And I have high cardinality categories, it will call the gap encoder. If I have date or times, it will call a specific datetime encoder. And all this can be configured, but it's very, very easy to use. So, if we go back to the challenges of our data tables that I mentioned, we have heterogeneous columns, we may have missing values, we may have open-ended strings, we may have date times, we have all these things. And what we find is that a combination of tree-based models such as scikit-learn's his gradient boosting and specific column encoding such as what you get with skrub table vectorizers works extremely well. And skrub comes in with a very, very simple function, tabular learner, that builds a model, that really helps you build a model for regression, for classification, given specific learners. If you can, for instance, use a linear model or a gradient boosting model, and that the resulting model actually can readily fit and predict and be cross-validated and everything directly on data frames, directly on tables. So hopefully this really, really helps working with data frames, doing machine learning with data frames and tables. Okay, now I want to come back to neural networks. So we haven't had success in the experiments that we did earlier. But if you look at the successes in vision, for instance, or in language processing, these were either driven by very, very large data sets or by using pre-trained models. So we don't have very, very large data sets. Our typical applications and data science don't have very, very large data sets. So what we need to do is to enable pre-train. Okay, how can pre-training work for data tables? If I give you this bunch of number, what can you tell from it? Not much. And that's a different thing from if I give you a typical image or a typical text. You can tell a lot from it. And now, if I give you this table, it's the very exact same table of number, but it comes with text in column names, text in the categorical columns, maybe a title. Now I have much more prior information. Now I can tell much more, and I can start maybe finding things that might be errors. I can have priors on the kind of distributions that are meaningful. I could, for instance, compute the body mass index. So we are convinced that if there is to be a chat GPT moment for tabular learning, it will come from contextualizing the numbers with the associated strings. So really the idea is that if I want neural networks to bring value to your typical tabular data, it needs to be pre-trained. But here we have quite a challenge, which is that of data integration across table, a challenge that has been studied a lot in the database community. So data integration across tables needs to bridge many difficulties. The first one is entity matching. Different tables will call the same thing with different names. Another one is schema matching. Different tables will come with different colors, columns, different ways of representing the information. And we tackle this by doing local models of relational graphs. I'll explain what this means later. And with these tools and a bit more, we're able to pre-train models on very, very large data sources. And by very, very large data sources, I mean that we take representation of general knowledge in common knowledge graphs, basically database representations of what's on Wikipedia, and we pre-train our model on this so that the model captures all kind of different background information. Okay, so this is something that we've done recently in a research paper that we call CART, which is basically a pre-trained tabular transformer. And what it does is it does a graph representation that can bridge tables. So the idea being that we represent all the data as local graphs where the value of an entry in a table is the value of a node, and the type of the column actually appears as a type of edge. So this trick is a way of representing all kind of tables, including multiple tables linked together in relational databases in the same data structure. And that way we can fit all kind of tables jointly. And then on top of this, we use a graph transformer architecture because now that we have a graph, we can use graph neural networks. And so we pre-train this on very, very large knowledge bases using contrastive learning, basically contrasting likely graphs from unlikely graphs. To have this working, we need to contribute a new attention mechanism that accounts for relational information. The idea being that, for instance, the relation father of is not the same thing as the relation son of, and we need to differentiate those two relations. And so it's basically accounting for the column name. This is useful because it brings context or enrichment to data. So it's particularly useful in data where we have many string entries like the data that I showed you before. So I'm super excited about this because this could be the birth of tabular foundation model. So CART, by the way, stands for context-aware representation of table entries. What this is it's a pre-trained tabular transformer. So really what it does, even if you didn't understand all the little details that I described just before, is that it recontextualizes the table entries. So by doing this, it gives you a number and it captures the context of its number, which means it captures the meaning of its number. This opens the door to using knowledge accumulation for tables. And this is what enabled foundation models like ChatGPT. So basically, knowledge accumulation, but in text. So I'm personally super excited. There will be many iterations of this, but we're potentially seeing the kind of revolution that happened before for tables. All right, so I've sold you the ID. Does it work in real life? Those are empirical evaluations that we did in the paper that we published. And so, basically the more you're on the side, it's a ranking. So the more you have small numbers, the best you perform. And what you can see is that CART performs significantly better than a huge amount of baselines, including very, very strong baselines from the gradient boosting literature, such as CAD-Boost, including other neural net approaches, such as TAP-BFN, including using large language models to vectorize the tables. So it's when I look at this, I'm like, well, we do have something that looks like a fairly robust game. And what's really useful is that it can actually start doing things that we couldn't do before, which is, for instance, to fine-tune CART on multiple tables together. So I have multiple tables and they have only partial matching. They don't have the full set of similar information. I may have restaurant ratings from one data set and restaurant ratings from another data set. And because of the architecture that implicitly finds a common representation across the tables, then it can start fitting across the multiple tables. So this is super exciting and it outperforms the other way of doing things that are quite hacky. Okay, so to zoom out, I'm super excited about two different developments. One is skrub, which is really software that bridges databases to scikit-learn. It's really about preparing tables for scikit-learn, and it's going to go further than what I've shown. It's starting to do database operations, but in a way that can easily be put in a machine learning pipeline that can be optimized. It has pipelines that allows things such as joins and aggregation, and those pipelines are optimized for columnar operations. But it's not only optimized for database-ish things, it's also optimized for learning. So it can do things such as supervised, well, it will be able to do things in the near future, such as supervised join discovery. It is able to do vector representation of strings of fuzziness, just like the gap encoder that I showed. It comes in with little helpers, such as the table report. I have a few minutes, so let me show you the table report. Uh, So here I'm in a Jupyter notebook, and here I've just I have a data frame, and here I've just display the table reports of the corresponding data frame. And the thing is, it's an interactive thing. I can inspect the different tables, the different columns each time I get useful information. I can get full description of all the column summaries, and it even tells me information such as, wait a second, the column department and the column department name are actually extremely similar. They're pretty much the same information. So, that's the kind of thing we're working in Scrub, just to make your life easier. So, Scrub is very new. Much more will happen in Scrub, but I think it fills a very, very important niche. Scrub is, in a sense, simple technology. And when I say simple technology, it's a good thing in my words, because it's easy to install. It doesn't require large hardware. It can be run by anybody. On the other end of the spectrum, I'm also super excited about the foundation models. The card foundation model that I presented, which is basically a transformer that combines strings, numbers, and relations in the sense of relational databases. And this really has the possibility of unlocking foundation models, so very powerful models that work on tabular data and relational databases. We'll see where it goes. There will be many developments in the near future. Thank you for listening. I'm available for questions.